calculus students, how you doing today? We are working on section 1.4b, discontinuity. We will abbreviate that with a DC in a circle so we don't have to keep writing that. And the intermediate value theorem, the IVT. This is a theorem that is used on the AP exam. You will use it in some of your reasoning when you do free response questions on the AP exam. Without a doubt, this will be one of your reasons due to the intermediate value theorem, the IVT. I will be asking you in class for these conditions and what the conclusion is, because it's very important to know these. So now that we studied continuity in 1.4a and talked about the continuity test, remember the three parts to that. A point has continuity if the point exists, if the limit exists as you approach that x value, and if 1 and 2 are equal to each other. So what happens if you have a discontinuity? What does that look like? Today we're going to talk about removable and non-removable discontinuities. Okay, so what if you do find a discontinuity? What type of discontinuity is it? Non-removable, we call that an NR with a circle, DC, so we don't have to keep writing that huge phrase. So a non-removable discontinuity means that the limit as x approaches c does not exist, d any, and you cannot write a simpler function. In other words, you have the limit as x approaches -2 of 1 over x plus 2. Okay, here's a graph of 1 over x plus 2. Obviously, when you try direct substitution of a -2 into the limit, because this is a continuous function everywhere on its domain, just not right here, then when we try direct substitution, we can't find that limit, whether it exists or not. Notice also, though, that there's no algebra we can do. We can't do any dividing. We can't do any canceling to remove this problem we have with using direct substitution. And so we say that this is a non-removable discontinuity. I can't do any simpler math. So let's go back. The limit does not exist, and you cannot write a simpler function, or you can write a simpler function, but the limit as x approaches c of f of x still does not exist. It doesn't get rid of the problem. Okay? This is called an infinite or unbounded discontinuity. And then graphs or functions with non-removable discontinuities may also be piecewise functions with a jump discontinuity. So notice here, in this graph here, there is not a limit that exists at this c right here, nor this is a horizontal line and a y equals mx plus b line, nor is there a way I can simplify to remove a problem, a discontinuity. Okay, and we will do practice with this, with these problems. There will be a second video on examples looking at non-removable and removable discontinuities. So what is a removable discontinuity? That would be an R with a circle and a DC with a circle. In this case, the discontinuity itself is not removed. You can't ever, that's it, the discontinuity is gone. So what's removable about it? What's removable is that a different discontinuity results. In this case, the limit as x approaches c of f of x does exist, but f of c does not exist, so you can't use direct substitution. However, you can write a simpler function. Here's my example. The limit as x approaches -1 of this expression. Here is a graph of it, okay? So notice that when you try to put a -1 into this function, it does not exist, right? F of c doesn't exist. But when you look, as you approach this x of -1, there does seem to be a limit. And in fact, here we could do some simplification. This numerator could be written as x plus 1 times x plus 1. And if we divide by x plus 1, notice that we have removed the factor that is causing us the issue of evaluating the limit, and now we can use direct substitution. So let's go back. You can write a simpler function and evaluate the limit. You will see an expression canceled, removed from the original function, so you can use direct substitution to find the limit. This discontinuity shows up as a point discontinuity at x equals c, right there, a point discontinuity. And so we're going to do examples, an example video, these three problems here. So let's recap. You have a discontinuity. It's been identified that you have one. And there's two types. Non-removable means that there is a discontinuity and you can't write a simpler function to evaluate a limit because it doesn't exist. Here, a removable discontinuity. There is still a discontinuity, but you can, the limit does exist. You can write a simpler function and remove the factor that's making it impossible for us to use direct substitution. Now you can, and you can evaluate the limit. The discontinuity still exists. Now, the second part of 1.4b today is the intermediate value theorem. And the reason why we're studying it today is because it does involve continuity. And so we are going to bring what we have learned together into this theorem here. The IVT, there's a theorem 1.1 in your textbook on page 777. Sorry, 77. It's been a long day. In case you want to read that yourself. But here it is. Okay, these conditions are very important. So A, if f of x is continuous on a closed interval, so you need these two things. If the function is continuous on a closed interval, notice that is true in this picture. You have a continuous function on a closed interval. That is true on this graph. You have a continuous function on a closed interval. Look at those endpoints. Notice that is true here. Continuous function on a closed interval. Second, f of a does not equal f of b. Let's take a look. F of a, f of b. Notice they are not equal to each other. Those are different y values. F of a does not equal f of b. F of a does not equal f of b. Notice that these three graphs meet the conditions we have read. And k is any value between f of a and f of b. Notice f of a and f of b are y values. A and b are x values. So the k is a y value. So k is any value between f of a and f of b. Let's check our pictures. F of a, f of b, yes, we have a k in between. Is it directly in between? It doesn't have to be. Here's f of a and here's f of b. Notice k is in between, but it doesn't mean that it's in the middle of those two exactly. F of a, f of b, here's a k in between. Okay, what we can conclude from these three conditions is then there is at least one x equals c where the value of the function does equal k. It is guaranteed, it has to happen. What does that mean? Let's recap. If you have a function that is continuous on a closed interval, f of a does not equal f of b, and k is a y value in between f of a and f of b, then there we can conclude without a doubt there is at least one x that we call x equals c where f of c equals k in between f of a and f of b. Let's take a look. Here's a picture that meets all the three conditions we talked about. Let's take a look. Here's a k, and here's the c where it happens. It is guaranteed that there is a c value where the function has a y value of k. Take a look here. Here's our k, in between f of A and f of B, it is guaranteed there is a C in between A and B that makes this happen. Let's take a look. Here's our K, let's go across. It is guaranteed at least once, but it could be a lot more times, that there is a C between A and B that makes the value of the function equal K. Look at it, happens here, it happens here, it happens here, and here, and here. It is guaranteed there's a C between A and B at least once. It can happen many times, okay? Now, what does this look like in the real world? Why does this have to be true? Think about this. Here's a real world example. You are going 50 miles an hour at 2 hours on a trip and 70 miles an hour at 4 hours on your road trip. So you're on a road trip at 2 hours, you're going exactly, you notice you're going exactly 50 miles an hour. Okay? 4 hours into your trip, you take a look, you see you're going exactly 70 miles per hour. Is it guaranteed that you were going exactly 65 miles an hour at 1 or more times between 2 and 4 hours? Yes, it is. If you were going 50 miles per hour at 2 hours and then later you were going 70 miles an hour, didn't you at some point have to be going 65 miles exactly to go from here to here between that time? It's guaranteed. It has to be. Why? Because this situation is continuous. It's on a closed interval from 2 hours to 4 hours. F of A does not equal F of B, right? 50 does not equal 70. And the K value, 65, is in between F of A and F of B. It's guaranteed. You had to when you think about it. Logically, you had to. Okay? What's a non-example then? When would this not happen? This would not happen when the conditions are not met. Let's take a look at our non-example graph, and then we'll do our non-example wording. Let's take a look here. Notice on this graph, I'm checking my conditions. F of X is continuous on a closed interval. Nope. No, that's not happening. This is not a continuous graph because right here, where X is equal to A, the limit does not exist. It fails the second part of the continuity test, right? This is not a closed, a continuous function, okay? Certainly it meets other things. F of A doesn't equal F of B, and it meets other conditions, but it does fail the second part of the continuity test. This is not a continuous function. So watch what happens. Is it guaranteed that there's at least one X equals C in between A and B where there's a Y value of K? There's not. Take a look. Here's F of A, F of B. Here's K. Look at that. There's no X value where that K happens. It wasn't guaranteed because the conditions were not met. Here's a non-example in the real world. You have $1,000 in your bank at the end of August and $550 on September 19th. Is a balance of exactly $723 guaranteed during this time period? No, it's not, because when you take money out or put money in, it's not continuous. You don't have to go through every possible dollars and cents between 550 and 1,000. It jumps. It's not a continuous function. So it's not guaranteed that you had exactly $723 at some point during that time because it was not continuous. The conditions weren't met. So on our next video, there's going to be an example video. We're going to look at these problems here, and I hope you enjoyed section 1.4b.